Since time immemorial, humanity has looked up at the night sky and found among the sea of twinkling points a distinct reddish light that seems to pulse in an almost living way. Mars, the red planet, has always been more than just a distant celestial body. It is a symbol steeped in mystery, curiosity, and desire. The unusual color that shines through Earth's atmosphere made it stand out to ancient civilizations, sparking religious, mythological, and later scientific interpretations. At a time when knowledge about the cosmos was limited to visual observations and rudimentary records, Mars became an enigmatic beacon that fueled both fear and imagination. Its crimson hue was associated with blood, fire, and war, leading virtually all human cultures to link it with ideas of conflict and power. This association was not merely an aesthetic coincidence, it shaped narratives, influenced calendars, and inspired legacies that still echo to this day. The fascination with Mars is also the result of its relative proximity to Earth, making it one of the brightest and most easily observable objects to the naked eye. During certain periods, the planet comes closer to our world, becoming an intense point of light in the sky, which generated cycles of anticipation and observation among ancient civilizations. Early astronomers tracked its retrograde movements with perplexity, noticing that it did not follow the simple patterns other celestial bodies did. This apparent irregularity in Mars' motion across the sky helped to challenge geocentric conceptions, and long before the invention of the telescope, already hinted at the complexity of celestial mechanics. For many peoples, each return of that brighter red light in the sky was interpreted as an omen, whether of harvest seasons or times of war. In the symbolic realm, Mars also became a blank canvas for psychological and collective projections. Humanity, when looking upward, has always sought reflections of itself, and the red planet served as a cosmic metaphor for our own impulses and conflicts. Poets and philosophers saw in it an embodiment of destructive drive, but also of courage and determination. Its constancy, always returning to the same point in the sky, gave the impression that Mars not only existed physically, but also participated in some way in human life on Earth. This imagined bond was reinforced over millennia, creating an almost intimate relationship between the planet and our species. As the ages advanced, curiosity about Mars began to shift from the purely symbolic to the investigative sphere. Modern science, born from the desire to understand and classify the universe, found in the red planet an ideal target. It is close enough to be studied in detail and mysterious enough to raise fundamental questions about the origin and evolution of worlds. Throughout the 19th and early 20th centuries, even before probes or rovers, Mars held a prominent place in scientific conferences and astronomy articles, often competing for public attention with the advances in lunar discoveries. Its orange surface, marked by contrasts of light and shadow, seemed to suggest the presence of seas, continents, and perhaps even forms of life. But perhaps the most powerful element that keeps our interest alive is the possibility that Mars, at some point in its history, may have harbored life. Even though science still seeks concrete proof, evidence that the planet once had liquid water, active volcanoes, and a thicker atmosphere sustains the hope that we are not alone in the universe. This hypothesis not only fuels scientific research, but also inspires fiction, art, and entertainment, keeping Mars at the forefront of books, films, music, and games that explore everything from tales of lost civilizations to epics of interstellar colonization. The red planet, therefore, is not just an object of study, it is a mirror of our desire to push boundaries and understand humanity's place in the cosmos. Today, when we look at Mars through the lenses of advanced telescopes or in images captured by interplanetary probes, we carry with us the weight of thousands of years of fascination. Every pixel transmitted from its dusty plains and deep craters is more than scientific data. It is the continuation of a relationship that spans cultures and eras. Mars calls to us, and that call echoes not only in the halls of science but in the collective imagination, as a reminder that, despite our technological achievements, we are still the same dreamers who, in Antiquity, were hypnotized by that red light in the sky. Long before modern science existed, the human gaze toward the sky was driven by a mixture of reverence, fear, and curiosity. Among all the points of light crossing the celestial dome, Mars stood out as an unmistakable presence. Its reddish coloration was so unique that in virtually all ancient cultures it was associated with blood, fire, and violence. This symbolic connection to war, death, and courage shaped not only its name but also its role in the myths and rituals of the civilizations that observed it. In ancient Rome, the planet was named after Mars, the god of war and patron of soldiers, equivalent to the Greek Ares. This choice was no accident. In the Roman view, Mars represented not only destruction, but also military discipline, strategy, and protection of the homeland, aspects that match the image of an imposing and unchanging celestial body crossing the sky with determination. In the Greek world, Ares carried a darker symbolism. While Mars for the Romans was honored as a guardian of order, Ares represented the irrational fury of combat, raw and uncontrollable violence. Even so, in both cases, the red planet was perceived as an entity with power over the fate of men, influencing victories and defeats on the battlefield. This association was not limited to the Mediterranean. Among the Babylonians, Mars was known as Nergal, a god connected not only to war, but also to plagues and the underworld. Its crimson color and unusual brightness were interpreted as manifestations of destructive energy, and its presence in the skies could be seen as a portent of catastrophes. In ancient Egypt, the planet was called Her-Desher, meaning the Red One, highlighting its characteristic hue and associating it with gods who symbolized strength and endurance. In the East, Mars also occupied a central role in the celestial imagination. Ancient Chinese astronomers called it the fire star, Huoxing, incorporating it into a cosmological system in which each planet was linked to an element and a set of omens. During periods of its greatest visibility, when it shone intensely in the night sky, Mars was believed to herald political conflicts, rebellions, and dynastic changes. In pre-Columbian cultures, such as the Maya, observation of Mars was integrated into agricultural calendars and religious rituals. Carved records and codices show that its movement was tracked with precision, and its cycles served as markers for specific periods, influencing both ceremonies and strategic decisions. Beyond its religious and astrological significance, ancient civilizations also observed Mars as part of their studies of celestial motion. The planet, like the other so-called wanderers, a term used to designate celestial bodies that moved in the sky differently from the fixed stars, displayed a peculiar behavior, retrograde motion. During certain periods, Mars seemed to slow down, stop, and then move in the opposite direction before resuming its normal course. This phenomenon intrigued early observers and challenged simpler explanations, as it did not fit primitive geocentric models. For many, this irregular movement was interpreted as a sign that the planet possessed its own will, acting according to divine forces. The documentation of these observations, even if rudimentary, was essential for the evolution of astronomy. By recording Mars' positions over the years, Babylonians, Egyptians, and Greeks began to perceive more complex patterns in celestial motion, which, centuries later, would form the basis for orbital calculations. In the absence of telescopes, all knowledge of the planet came from meticulous notes and the oral transmission of knowledge, often blending astronomical facts with mystical interpretations. This fusion of early science and belief shaped humanity's relationship with Mars for millennia. Thus, even before we knew that Mars is a world with colossal mountains, immense canyons, and traces of water, it was already an active character in human history. It served as a guide for navigators, a marker for farmers, an inspiration for warriors, and an object of devotion for priests. This constant and multifaceted presence explains why, even after the scientific revolution, the aura of mystery surrounding the red planet did not disappear. On the contrary, it adapted, migrating from mythology to science, but keeping alive the same flame of curiosity that burned in the eyes of our ancestors when they looked to the sky and saw that crimson light cutting through the darkness. For centuries, observations of Mars were limited to the human eye and the aid of simple instruments such as astrolabes and quadrants. This began to change radically in the early 17th century, when the telescope, still a rudimentary but revolutionary invention, paved the way for a new phase in the history of astronomy. It was during this period that the red planet ceased to be merely an intriguing point of light in the sky and became a visible world, with surface details, phases of illumination, and clues about its true physical nature. Among the pioneers of this new era was Galileo Galilei, who in 1609 pointed his primitive telescope toward Mars and for the first time saw a defined disk rather than a simple reddish star. Although his lenses were still unable to distinguish complex features, the mere realization that Mars had shape and variations in brightness already indicated that it was a solid planet, illuminated by sunlight. Shortly afterward, other astronomers began to improve their observations. In the 17th century, Christian Huygens, known for discovering Titan, Saturn's largest moon, produced drawings showing dark patches on the Martian surface. He was also the first to estimate the length of a Martian day with remarkable accuracy, arriving at a value very close to the 24 hours and 37 minutes we know today. This information was a milestone. For the first time, the rotation of a planet beyond Earth was determined, reinforcing the idea that Mars was in many ways similar to our own world. A few decades later, Giovanni Domenico Cassini refined these measurements and confirmed the existence of the polar caps, observing that their size varied as the Martian seasons changed, an indication that the planet went through climatic cycles. In the 18th century, optical technology continued to advance, allowing astronomers such as William Herschel to make more detailed observations. Herschel, famous for discovering the planet Uranus, studied Mars extensively and concluded that its polar caps were composed of ice, not clouds or rocky formations. He also suggested that the planet's thin atmosphere allowed for seasonal changes similar to those on Earth, leading many to speculate that Mars might harbor life forms. This idea would become even more popular in the 19th century, especially when telescopic observations revealed supposed canals crossing its surface, linear structures that some at the time believed to be the work of an intelligent civilization. The classical era of astronomy was not limited to recording physical details. It also produced a growing body of fundamental astronomical measurements. Using parallax, astronomers calculated more precisely the average distance between Earth and Mars, which helped establish the true scale of the solar system. Observations of oppositions, moments when Mars and Earth are closest in alignment with the Sun, became strategic opportunities to map its surface and refine orbital calculations. The discovery of Mars's two small moons, Phobos and Deimos, by Asaph Hall in 1877 was another significant step, further fueling scientific interest in the planet. Although the technological limitations of the time still imposed considerable margins of error, the telescope era solidified the image of Mars as a dynamic world, potentially similar to Earth. This period also marked the transition from purely astronomical curiosity to more intense speculation about its habitability. Each new spot observed, each shadow cast upon its plains, fed hypotheses ranging from geological explanations to dreams of alien cities. Thus, the telescope not only brought Mars closer to our eyes, but also expanded the reach of human imagination. By the end of the 19th century, Mars was no longer just a distant and mysterious object, but a neighbor whose terrain, climate, and even day length we had begun to know. The detailed observations of this era paved the way for future space explorations, which, in the following century, would finally give us close-up images and answers to many of the questions that the earliest telescopes had only hinted at. The 19th century marked a turning point in the study of Mars, not only because of the advancement of telescopes, but also due to the emergence of one of the most influential and controversial interpretations in the history of astronomy. The idea that the Martian surface was crossed by a network of artificial canals, possibly built by an intelligent civilization. It all began in 1877, when Italian astronomer Giovanni Schiaparelli, during a particularly favorable opposition of Mars, observed and recorded linear features crossing the planet. He called them canali, an Italian term meaning channels or natural waterways, but when translated into English it took on the meaning of canals, man-made constructions. This simple linguistic slip fueled a wave of speculation that would last for decades. Schiaparelli's illustrations showed dozens of straight lines, many of them connecting dark patches he interpreted as seas or lakes. He believed these structures could be natural formations, but translation and popular imagination soon distorted his original intent. The idea gained momentum when, in the United States, astronomer and writer Percival Lowell embraced the hypothesis that the canals were feats of colossal engineering, built by an advanced civilization struggling to survive on an arid planet. Lowell invested his fortune in building an observatory in Flagstaff, Arizona, specifically to study Mars, and published books detailing how these supposed canals transported water from the polar caps to the rest of the planet. Lowell's vision was welcomed with enthusiasm by the public and the press, but met with skepticism by many scientists. Even so, the idea of a Martian civilization took strong hold in the popular imagination. Newspapers and magazines reproduced maps filled with lines, and science fiction writers such as H.G. Wells found inspiration to craft narratives blending science and adventure. The War of the World, 1898, did not describe canals directly, but it portrayed Mars as the home of a technologically superior alien race, reinforcing the association between the planet and extraterrestrial intelligence. Enthusiasm, however, was not universal. Experienced astronomers such as Edward Maunder argued that the lines seen by Lowell and others could be optical illusions caused by the limitations of the telescopes of the time and by the human eye's tendency to connect isolated points into linear patterns. Tests showed that different observers, looking at the same region of Mars, often drew maps with canals in different positions, suggesting that subjective perception played an important role. Nevertheless, the controversy persisted, as not everyone agreed that they were merely visual artifacts. The Martian canals became a cultural phenomenon. They appeared in public lectures, exhibitions, and even in children's toys and games. This popularization deeply influenced the way the public viewed the planet, transforming it from a mere cosmic neighbor into a hypothetically inhabited world. This romantic and technological vision of Mars helped sustain interest in its exploration throughout the 20th century, helping justify investments in astronomical research and later in space missions. It was only with the arrival of space probes in the 1960s, such as Mariner 4, that it was definitively proven that Lowell's canals did not exist. The images sent back showed an arid planet, full of craters and without any network of linear structures. Even so, the canals episode left a lasting legacy. It demonstrated how mistaken interpretations, combined with humanity's desire to find life beyond Earth, can shape our perception of reality. This blend of science, error, and imagination set the stage for Mars's transition from an object of speculation to a target of direct investigation, without, however, erasing the charm of the old stories about a lost civilization struggling to survive on the red planet. Long before we had actual photographs of the surface of Mars, the red planet already held a prominent place in the arts, literature, and the collective imagination. During the late 19th century and the first decades of the 20th, the influence of astronomical observations, especially the controversy over the canals, spread beyond science, permeating narratives ranging from adventure romance to the boldest science fiction. It was during this period that Mars ceased to be merely an object of study and became a vivid setting where entire stories unfolded, with its own peoples, cultures, and conflicts. One of the first and most striking examples of this transition was the classic The War of the Worlds by H.G. Wells, published in 1898. Inspired by both fascination and fear of the unknown, Wells created a narrative in which Martians, described as beings of high intelligence and technology, invade Earth in search of resources, exterminating human populations with far superior weapons. The novel not only popularized the idea of an advanced Martian race, but also reflected the social and political anxieties of the time, especially European colonialism and the rapid changes of the Industrial Revolution. The work's success was so great that decades later, in 1938, its radio adaptation by Orson Welles would cause real panic among listeners who believed they were witnessing a genuine invasion. At the same time, other authors explored Mars as an exotic and mysterious place. Edgar Rice Burroughs, creator of Tarzan, released A Princess of Mars in 1912, the first book in his Barsoom series. In these stories, Mars was portrayed as a world inhabited by different races, filled with political intrigues, epic battles, and stunning landscapes. Although scientifically inaccurate, these narratives fueled the romanticism surrounding the planet, presenting it as a destination for adventure and heroism. The success was such that the series extended for decades, directly influencing cinema and television in the years that followed. Silent cinema also embraced the Martian aesthetic. Experimental films and science fiction shorts from the first half of the 20th century often depicted imaginary journeys to the planet, frequently blending fantastical settings with elements inspired by Percival Lowell's maps. These productions, though limited by the special effects of the time, helped cement the image of Mars as a place of mystery and danger. In comic books, pulp magazines, and radio serials, Martians appeared sometimes as menacing villains, other times as benevolent allies, reflecting the shifting political and cultural moods of the century. The period was also marked by a strong overlap between science and speculation. Lecturers and writers promoted their visions of Mars as a planet with seasonal vegetation, dried oceans, and colossal constructions. Popular science magazines published colorful illustrations, often imagining futuristic cities on the Martian plains. This visual imagery became so influential that even after the first photos from space probes revealed a much drier and more inhospitable landscape, many people continued to refer to Mars as the planet of canals and lost civilizations. This constant presence in popular culture made Mars a multifaceted symbol. It could represent both threat and hope, the possibility of interplanetary war, and the dream of contact with other forms of life. Stories set on the planet functioned as metaphors for universal human concerns: the fear of the unknown, the desire to explore, and the need to understand what lies beyond our borders. At the same time, fascination with the planet helped keep the flame of scientific curiosity alive, motivating new generations to look up at the sky and ask, what if something is out there? Thus, long before technology allowed us to land probes on Mars or explore its plains with robotic vehicles, the red planet had already secured a firm place in the realm of human imagination. It was, and in some ways still is, a mirror onto which we project our greatest fears and our boldest dreams of the future. Mars, the fourth planet from the Sun, is one of the most studied and fascinating worlds in the solar system. Its geography and physical characteristics combine elements familiar to Earth with unique aspects that make its scientific exploration even more compelling. With a diameter of approximately 6,779 kilometers, Mars is about half the size of Earth, but its total surface area is close to the land area of all the continents combined. Its gravity is only 38% of Earth's gravity, which means that an object or person on Mars would weigh just over a third of what they weigh on Earth. This difference profoundly influences how a human would move on the planet and how artificial structures would need to be designed. The mass of Mars is about 10% of Earth's mass, and its average density is 3.93 grams per cubic centimeter, lower than Earth's due to the smaller amount of heavy metals in its core. Mars takes 687 Earth days to complete an orbit around the Sun, defining a Martian year. However, its day, called a sol, lasts 24 hours, 39 minutes and 35 seconds, meaning that for an astronaut, the Martian rotation would be almost indistinguishable from Earth's. This similarity in day length is one of the factors that fuels the idea of colonization, as it would make it easier for the human biological cycle to adapt. Mars's rotational axis is tilted about 25.19 degrees, very close to Earth's tilt of 23.44 degrees. This means that the planet also has seasons, although they are almost twice as long due to its longer year. However, Martian seasons are more extreme in terms of temperature and variation in the size of the polar caps. The planet lacks liquid oceans to help regulate the climate as Earth's do, which contributes to sharp thermal fluctuations between day and night. The Martian surface shows a remarkable contrast between the northern and southern hemispheres. The north features vast, relatively low and smooth plains, known as the northern lowlands, which may have been ancient ocean beds. The southern hemisphere, on the other hand, is higher, more rugged, and filled with impact craters, some billions of years old. This hemispheric asymmetry is one of Mars's most intriguing geological features and remains the subject of intense study to understand its origin. Among the planet's most impressive formations is Olympus Mons, the largest volcano and tallest mountain known in the solar system. Standing about 22 kilometers high and spanning 600 kilometers in diameter, it is almost 3 times taller than Mount Everest, and so wide that, if placed over Western Europe, it would cover entire countries. Another colossal structure is Valles Marineris, a canyon system stretching over 4,000 kilometers in length and reaching depths of up to 7 kilometers. For comparison, it is 10 times longer and several times deeper than the Grand Canyon in the United States. Mars also has polar caps composed mainly of carbon dioxide ice, dry ice, and to a lesser extent, water ice. These caps expand and contract as the seasons change, releasing and trapping gases in the atmosphere, which affects the planet's global atmospheric pressure. The Martian terrain also features vast sand dunes, fields of broken rocks, dry valleys resembling riverbeds, and plains covered in fine dust, the result of billions of years of erosion and meteorite impacts. Another important characteristic is that Mars has an extremely weak magnetic field, localized only in certain regions of the crust, unlike Earth's strong global field. This lack of significant magnetic protection means that the planet is more exposed to cosmic radiation and solar wind, critical factors for any plan of human colonization. The thin atmosphere, composed mainly of carbon dioxide, further contributes to this vulnerability. In terms of internal composition, Mars is thought to have a core likely made of iron, nickel, and sulfur, surrounded by a silicate mantle and a relatively thin crust. Current geological activity is low, but there is evidence that volcanoes remained active longer than previously thought, and some studies suggest there may still be enough heat inside to generate occasional subsurface activity. These physical and geographical characteristics not only make Mars a fascinating object of study, but also place it at the center of discussions about the habitability of worlds beyond Earth. Its monumental relief, signs of a possibly wetter past, and partial similarities to our planet fuel both science and imagination, cementing its role as the leading candidate for a future human presence in the solar system. The climate and atmosphere of Mars are crucial elements for understanding not only its geological history, but also its potential to harbor life and sustain future human missions. Unlike Earth, which has a thick and protective atmosphere, Mars is surrounded by an extremely thin layer of gases, with an average surface pressure of only 0.6% of Earth's atmospheric pressure at sea level. This drastic difference means that, in practice, the Martian atmosphere is almost a vacuum, unable to retain heat efficiently or to protect the surface from cosmic and solar radiation. The composition of this atmosphere is dominated by carbon dioxide, which makes up about 95% of its volume, followed by small amounts of nitrogen, argon, oxygen, and traces of water vapor and methane. This high CO2 concentration, however, does not create a significant greenhouse effect as it does on Earth, precisely because the atmospheric density is so low. This results in average temperatures of approximately -63 degrees Celsius, with extreme variations. During the day near the equator, temperatures can reach just over 20 degrees Celsius, but at night they drop to -73 degrees Celsius or lower. In polar regions during the Martian winter, temperatures can fall below -125 degrees Celsius, freezing part of the atmosphere itself into dry ice. The low density of the atmosphere has another striking effect. The Martian sky appears in shades different from those we are used to on Earth. During the day, it tends to have an orange or yellowish hue, the result of sunlight scattering through the fine dust suspended in the air. In contrast, during sunset, the horizon near the sun takes on a bluish tint due to preferential scattering of light in that specific range. This visual inversion, a bright orange daytime sky and bluish sunsets, is one of the most iconic features recorded by probes and rovers exploring the planet. Another characteristic climatic phenomenon on Mars is the occurrence of dust storms, which can range from local whirlwinds to global events that envelop the entire planet for weeks. These storms are driven by winds that can reach up to 100 kilometers per hour, but due to the low air density, they exert far less force on objects than winds of the same speed on Earth. Nevertheless, the fine electrostatically charged dust can cover solar panels and impair exploration systems. Global storms, such as those recorded by the Mariner and Viking probes, obscure the surface and drastically reduce visibility, temporarily altering the planet's thermal balance. The seasonal cycle on Mars is more pronounced than on Earth in some aspects, and milder in others. This is due to the combination of its axial tilt of approximately 25.19 degrees with its more eccentric orbit. The result is that the seasons are not of equal duration, and the hemispheres experience asymmetrical seasonal variations. For example, Summer in the southern hemisphere is shorter but warmer due to Mars' proximity to the Sun at that time, while summer in the northern hemisphere is longer but slightly cooler. Another point of interest is the intermittent presence of methane in the Martian atmosphere. Observations made from both Earth and orbiting spacecraft have detected seasonal and even localized variations in methane concentration, raising important questions. It could result from geological processes such as serpentinization or from biological processes such as microbial activity. Although no conclusive evidence has been found, the mere detection of this gas sparks great interest, since on Earth, most atmospheric methane is of biological origin. In addition, the Martian atmosphere plays a key role in the planet's water cycle. Small amounts of water vapor can condense and form clouds, usually composed of water ice or, at higher altitudes, carbon dioxide ice. These clouds, when observed by rovers, can take on fascinating shapes such as long plumes or wavy patterns, reminiscent of terrestrial phenomena, but adapted to the Martian context. Combining extreme temperatures, low pressure, peculiar gas composition, and weather events such as dust storms and pronounced seasonal variations, Mars presents a challenging environment for any attempt at human occupation. Even so, these very aspects make it a natural laboratory for understanding atmospheric processes on rocky planets and for investigating the limits of habitability beyond Earth. The surface of Mars is at once familiar and alien to the human eye. Seen up close through the cameras of probes and rovers, it reveals a landscape reminiscent of Earth's deserts, but with unique colors, textures, and structures shaped by billions of years of geological activity, cosmic impacts, and erosion. The planet presents a complex mosaic of formations, vast plains, impact craters of varying sizes, canyons rivaling the largest on Earth, undulating dunes, and colossal volcanoes that surpass any mountain known on our planet. Mars's characteristic coloration, ranging from orange to deep red, is the result of the oxidation of iron minerals present in the dust and rocks on its surface. This process, which created the planet's famous rusty appearance, has been taking place over millions of years. Constant winds combined with dust storms help spread this thin layer of iron oxide across the entire surface, unifying the Martian palette and contributing to its nickname, the Red Planet. Geologically, Mars can be divided into three major regions: the plains of the northern hemisphere, the highlands of the southern hemisphere, and the volcanic and tectonic regions. The northern hemisphere is dominated by low-altitude, gently sloping areas, such as the northern plain, Vastitas Borealis, which may have been the bed of a primitive ocean. The southern hemisphere, on the other hand, is older and heavily cratered, with terrains dating back over 4 billion years, preserving records of the earliest impacts that shaped the planet. This hemispheric asymmetry is one of the largest in the solar system and raises hypotheses of a past marked by catastrophic events, such as the impact of a massive body that could have reshaped the crust. Among the most impressive formations is Olympus Mons, the largest known volcano, standing 22 kilometers high and 600 kilometers in diameter. Surrounding it are other large volcanoes such as Ascraeus Mons, Pavonis Mons, and Arsia Mons, forming the Tharsis region, a vast tectonic uplift stretching for thousands of kilometers. Volcanic activity on Mars was likely intense in its past, and although no recent eruptions are known, there is evidence that some volcanoes may have been active geologically as recently as a few million years ago, a blink of an eye in planetary terms. Another highlight is Valles Marineris, a gigantic canyon system that cuts across the planet for more than 4,000 kilometers in length and up to 7 kilometers in depth. Its formation is linked to fractures in the crust caused by tectonic and volcanic forces, possibly related to the uplift of the Tharsis region. Within Valles Marineris lie narrower valleys, steep escarpments, and sedimentary deposits that may contain clues about Mars's past climate. Impact craters are abundant and range from small depressions to colossal structures like the Hellas Basin, about 2,300 kilometers in diameter and 7 kilometers deep. Formed by an impact billions of years ago, this basin is so deep that the atmospheric pressure inside it is significantly higher than in other parts of Mars, though still much lower than on Earth. Impact regions such as Hellas and Argyre are also important because in some cases they show signs that liquid water may have flowed after the craters formed. The planet also hosts vast dune fields, such as those found in Gale crater, explored by the Curiosity rover. These dunes move slowly under the action of Martian winds, providing information about weather patterns and atmospheric dynamics. In older areas, dry riverbeds and channels carved by water indicate that Mars once had an active hydrological cycle with flows that shaped the terrain. Mineral deposits such as hematite and sulfates reinforce this idea of a wetter past. The Martian crust is composed mainly of basalt, a volcanic rock also common on Earth. However, due to the absence of plate tectonics as we know them, geological formations on Mars remain stable for extremely long periods. This means structures billions of years old are still preserved, making the planet a valuable geological archive for studying the history of the solar system. Another striking element of the Martian surface is the presence of seasonal polar caps made of carbon dioxide ice and water ice. During winter, these caps expand to cover vast areas, and in summer part of the ice sublimates, releasing gases into the atmosphere. This dynamic influences the planet's global atmospheric pressure and is one of the drivers of its seasonal changes. The geological formation of Mars is the result of processes involving volcanic activity, meteorite impacts, wind erosion, and, in earlier times, water erosion. This combination has made Mars a world with an active past and a seemingly calmer present, but one that still holds secrets deep within its crust and in the marks etched across its surface. The presence of water is one of the most decisive factors for the habitability of any planet, and on Mars, it plays a central role both in understanding its past and in shaping expectations for its future. Today, Mars is a cold and arid world, with a thin atmosphere that makes the stable presence of liquid water on the surface impossible. However, multiple geological, chemical, and mineralogical lines of evidence show that, in remote eras, water was not only present but flowed abundantly across the Martian surface, forming rivers, lakes, and possibly oceans. The first clue came from images captured by the Mariner and Viking probes in the 1970s and 1980s, which revealed river valleys, outflow channels, and geological formations resembling deltas and dry riverbeds. These structures were very similar to those formed by erosive processes on Earth, strongly suggesting that liquid water played an active role in shaping the Martian landscape. Later studies indicated that about 3 to 4 billion years ago, during the so-called Earth's Noachian period, Mars had a thicker atmosphere and milder temperatures, conditions that would have allowed stable liquid water to exist on the surface for long periods. More recent evidence obtained by rovers such as Opportunity, Curiosity, and Perseverance reinforces this view. Hydrated minerals such as clays and sulfates have been found in various regions, indicating prolonged contact with water in the past. Curiosity, for example, analyzed sedimentary layers in Gale crater that point to the existence of a lake that lasted millions of years, with different depths over time. Perseverance, exploring Jezero crater, found clear evidence that a river system once flowed there, forming a delta filled with fine sediments, exactly the kind of environment where signs of microbial life could be preserved. Today, most of Mars's water is frozen. The polar ice caps, composed mainly of carbon dioxide ice, hide large reserves of water ice that have built up in alternating layers over millions of years. Furthermore, ice is not limited to the polar regions. Underground deposits have been detected in mid-latitudes and even near the equator, often buried beneath thin layers of soil and dust. In 2018, radar data from the European Mars Express probe indicated the presence of a subsurface lake of salty water beneath the South Polar Cap, about 20 kilometers wide. Although the extreme temperature and salinity make habitability difficult, this discovery shows that Mars still has liquid reservoirs in isolated conditions. Another important aspect is the presence of dicky, temporary brines. On the surface, under certain conditions, salts such as perchlorates can lower the freezing point of water, allowing small amounts to remain liquid for short periods. These brines can form seasonally, and although unstable, they represent a possible habitat for extremophile life forms similar to those found in cold deserts on Earth. The loss of much of Mars' liquid water is directly linked to the history of its atmosphere. Without a global magnetic field to protect it, Mars slowly lost its atmosphere to space due to the constant action of the solar wind. As atmospheric pressure dropped, water began to evaporate or sublimate more easily, migrating to the poles or becoming trapped underground. This process, which lasted billions of years, transformed Mars from a potentially blue planet into a frozen desert. The search for water on Mars is not just a scientific exercise, it is vital for planning future manned missions. Water is essential for human consumption, food cultivation, and fuel production through the separation of hydrogen and oxygen. Finding accessible sources of ice is a fundamental step for the feasibility of permanent bases on the planet. Thus, the water that once flowed freely across the Martian plains now survives in the depths and at the polar extremes as a distant echo of a more hospitable past. With each new mission, we uncover a little more of this lost water cycle, seeking answers not only about Mars's climatic history, but also about the possibility that, at some point, life may have found shelter on its ancient shores. The history of space missions to Mars is a reflection of humanity's persistence, creativity, and often frustration in the face of the challenges of interplanetary exploration. Since the 1960s, when the first attempts were made, up to the most sophisticated missions of the 21st century, the red planet has proven to be as fascinating as it is difficult to reach. Statistically, Mars is one of the most challenging destinations in the solar system. About half of all attempts to reach it have ended in failure, a constant reminder that traveling through space and landing on another world demands near absolute precision. The first attempt to reach Mars was made by the Soviet Union with Marsnik 1, launched in October 1960. This and other early missions failed before even leaving Earth's orbit or shortly after departure. Even so, each failure brought valuable technical lessons. The first major breakthrough came with NASA's Mariner 4 launched in November 1964. It became the first probe to successfully fly by Mars in July 1965, sending back 21 black and white images that showed a planet very different from the romantic visions of the time. Far from seas and vegetation, what was revealed were arid craters and a dry terrain reminiscent of the Moon. These photos ended many immediate hopes of finding advanced life, but opened a new era of realistic scientific study of the planet. In 1971, Mariner 9 became the first probe to enter Mars's orbit. Its arrival coincided with a global dust storm that obscured the surface for weeks. When the atmosphere cleared, Mariner 9's cameras revealed unprecedented images of giant volcanoes, immense canyons, and ancient riverbeds, forever transforming our understanding of Martian geography. That same year, the Soviet Union managed to land the Mars 3 High, the first probe to reach the surface, but contact was lost just 20 seconds after touchdown. Despite the failure, it was a historic achievement that marked humanity's first arrival on another planet beyond Earth. The next major milestone came with NASA's twin missions, Viking 1 and Viking 2, launched in 1975. Each mission consisted of an orbiter and a lander. The Viking landers were the first to transmit color images from the surface and to conduct scientific experiments directly on Martian soil. They analyzed the chemical composition of the terrain and performed biological experiments in search of signs of life. Although the results were inconclusive and still spark debates today, the Vikings set new standards for planetary exploration, operating for years and sending back valuable data. In the following decades, new attempts were made, but many failed, such as the Soviet Phobos 1's and Phobos 2 DAIS missions, and NASA's Mars Observer, which lost contact shortly before entering Martian orbit in 1993. The turning point came in the 1990s with the Mars Pathfinder mission, launched in 1996, which carried the small rover Sojourner, the first vehicle to move across the Martian surface. This mission was a resounding success, transmitting images and data that demonstrated the feasibility of exploration using mobile robots. Other notable orbital missions include the Mars Global Surveyor, 1996, which mapped the surface in unprecedented detail, and Mars Odyssey, 2001, which detected large amounts of subsurface ice. The European Space Agency's Mars Express, launched in 2003, contributed high-resolution studies and discoveries regarding the presence of hydrated minerals, reinforcing evidence of a watery past. Each of these historic missions was crucial in paving the way for modern exploration, providing detailed maps, climate data, and geological information that now support the latest generation of missions. They proved that Mars, though hostile and distant, is a possible target for human technology and a fertile ground for scientific discoveries of profound impact. The modern exploration of Mars represents the most sophisticated and ambitious phase of humanity's relationship with the Red Planet. After decades of attempts and learning, the beginning of the 21st century marked a transition from sporadic exploration to an almost continuous presence of probes and rovers, turning Mars into a real-time scientific laboratory monitored by different space agencies. Today, there are orbiters mapping the planet with meter-scale precision, rovers exploring specific regions in search of traces of life, and even drones flying in the thin Martian atmosphere, feats that just a few decades ago were considered impossible. A milestone of this new era was the 2003 launch of the twin rovers Spirit and Opportunity, part of NASA's Mars Exploration Rover program. Spirit landed in Gusev Crater, an area believed to have once been a lake, while Opportunity touched down in Meridiani Planum, a plain rich in hematite, a mineral that usually forms in aquatic environments. Designed to operate for only 90 days, both exceeded all expectations. Spirit functioned until 2010, and Opportunity, impressively, sent data until 2018, covering more than 45 kilometers on the surface. Together, they revealed geological evidence consistent with a wetter past, reinforcing the hypothesis that Mars once had habitable environments. In 2012, NASA raised the bar for exploration with the arrival of the Curiosity rover in Gale Crater as part of the Mars Science Laboratory mission. Curiosity is a true mobile laboratory, capable of analyzing rock and soil samples, measuring radiation, and studying the local climate. One of its most important discoveries was the identification of ancient river and lake environments that could have supported microbial life. It also detected seasonal variations in atmospheric methane levels, an intriguing finding that remains unexplained and could have both geological and biological implications. The modern era also introduced a new type of exploration, aerial. In 2021, alongside the Perseverance rover, the Ingenuity helicopter landed, the first powered aircraft to fly on another planet. With specially designed blades for Mars's thin atmosphere, Ingenuity performed experimental flights that demonstrated the feasibility of aerial reconnaissance on the planet. Perseverance's main goal is to search for signs of ancient life and collect rock samples for a future mission to return them to Earth. It landed in Jezero Crater, where an ancient river delta preserves sediments that may hold records of biological processes. In addition to surface missions, a fleet of orbital probes provides constant support. The Mars Reconnaissance Orbiter, 2006, delivers ultra-high-resolution images capable of spotting rovers on the surface. MAVEN, 2013, investigates how Mars lost its atmosphere over time, helping scientists understand its climate evolution. Other agencies are also part of this international presence. The European Space Agency's Mars Express has been active since 2003. India's Mangalyaan probe, 2014, demonstrated low-cost technological capability, and China's Tianwen-1, 2021, delivered the Zhurong rover, marking China's successful entry into Mars exploration with a landing and operational mission. These modern missions not only accumulate data, but also pave the way for an increasingly imminent goal, sending humans to Mars. More precise landing technologies, studies on local resources such as water ice, and experiments producing oxygen from the planet's carbon dioxide atmosphere, like the MOXIE instrument aboard Perseverance, are essential steps toward enabling crewed missions. With modern exploration, Mars has gone from being just a distant study point to becoming a world known in stunning detail. Today, we understand its seasons, storm patterns, rock composition, and the location of potential ice reserves. Yet the planet still keeps its secrets, especially about its habitable past and the possibility of life. And it is precisely this combination of answers and new questions that keeps Mars at the heart of space exploration plans for the coming decades. In recent years, Martian exploration has entered a phase of discoveries that not only confirm long-standing hypotheses, but also reveal completely unexpected phenomena. Thanks to the combination of rovers, orbital probes, and high-precision instruments, We are now able to see Mars with a level of detail unimaginable just a few decades ago. These findings are redefining our understanding of its geology, climate, history, and above all, its potential to have hosted, or still host, life. One of the most striking revelations concerns the presence of minerals formed in aqueous environments, found by rovers such as Curiosity and Perseverance. Inside Gale Crater, Curiosity identified extensive sedimentary layers composed of clays and sulfates, indicating that billions of years ago, long-lived lakes existed there. These environments would have been stable for millions of years, with chemical conditions favorable to microbial life. In Jezero Crater, Perseverance found geological structures typical of river deltas, with fine deposits that preserve sediments potentially rich in organic matter. Another major breakthrough was the detection of seasonal and localized variations in atmospheric methane concentrations. Curiosity recorded methane spikes that repeat annually, suggesting that there are active sources releasing the gas. While geological processes may explain part of this emission, the possibility that underground microorganisms are involved cannot be ruled out. This discovery is particularly intriguing because on Earth, most atmospheric methane originates from biological sources. In addition, data from the Mars Express probe and the Marsis radar have pointed to the existence of subsurface lakes beneath the South Polar ice cap, likely composed of liquid briny water. These liquid masses, maintained in a liquid state by high concentrations of salts, reinforce the idea that Mars may still harbor habitable environments underground. Further discoveries suggest that such deposits may not be exclusive to the polar region, but could also occur in mid-latitudes. Another area of progress is the study of recent geological activity. High-resolution images from the Mars Reconnaissance Orbiter show landslides, newly formed fissures, and debris flows that indicate Mars is still geologically active, at least on a local scale. Although there are no signs of current surface volcanism, evidence suggests that residual internal heat may drive underground processes, possibly influencing subsurface water circulation. Continuous observation has also revealed surprising atmospheric and climatic phenomena. The Opportunity rover documented local dust storms growing into global storms capable of enveloping the entire planet. Curiosity has observed high-altitude ice clouds and seasonal weather patterns that help to understand the dynamics of the Martian atmosphere. Perseverance, equipped with microphones, recorded the first sounds on Mars, from the wind to the operation of its instruments. Data that, beyond scientific curiosity, help study how sound propagates in a rarefied atmosphere. Another highlight is the discovery of rocks with high silica content and minerals altered by water, preserving microscopic structures that may hold records of past biological processes. These samples are being prepared for a future return to Earth in one of the most complex missions ever planned by NASA in partnership with ESA. Finally, a recent discovery by the Perseverance rover confirmed the presence of complex organic compounds in sedimentary rocks. While such molecules may have a purely chemical origin, their preservation in ancient aquatic environments is a promising sign for astrobiological studies. A detailed analysis of these samples, once returned to Earth, could answer central questions about the existence of life in Mars's past. These discoveries show that Mars is not a geologically dead or scientifically static world. It is a planet in constant transformation, with a past rich in interactions with water, active climatic processes, and a subsurface that may hold vital secrets. Each new mission not only expands our knowledge, but also strengthens the feeling that we are ever closer to answering the question that has driven our curiosity for centuries. Was Mars ever, or is it still, a living planet? The search for life on Mars is one of the most persistent driving forces in space exploration. Since the red planet began to be studied in greater detail, the question of its habitability, past or present, has become central to scientists, engineers, and curious minds around the world. This investigation combines data from geology, chemistry, climatology, and astrobiology, and involves hypotheses ranging from the existence of microbial life billions of years ago to the possibility of extremophile organisms surviving today in protected niches. From a historical standpoint, Mars offers several arguments in favor of a potentially habitable past. During the Noachian period, about 3.8 to 4.1 billion years ago, evidence suggests that the planet had a denser atmosphere, milder temperatures, and abundant liquid water on its surface. Rivers, lakes, and even a possible ocean in the northern hemisphere would have provided suitable chemical conditions for simple life forms, similar to terrestrial bacteria, to develop. Hydrated minerals found in various regions and sedimentary deposits preserved in craters support this view. The central question is whether such life actually arose and, if it did, whether it managed to survive the drastic changes that followed. When Mars lost most of its atmosphere, the climate cooled rapidly, liquid water disappeared from the surface, and cosmic radiation began to strike directly, creating a hostile environment. However, some scientists believe that even under such extreme conditions, life could have found refuge underground, where temperatures are more stable and radiation is significantly reduced. Subsurface niches with salty water, such as those suggested by orbital radar in the southern polar region, are top priorities for future astrobiological missions. Research into past or present life is also influenced by studies of terrestrial extremophiles, organisms that survive in conditions once thought lethal. Bacteria living in extremely dry environments, such as the Atacama Desert, or beneath ice and rock in Antarctica, demonstrate that life can persist in cold, arid, low-light environments. Other microorganisms withstand high doses of radiation or thrive in salt-saturated waters. These examples show that life does not need an idyllic setting to exist, only minimal and stable conditions to maintain metabolic processes. A particularly intriguing point is the detection of atmospheric methane on Mars, observed both by orbiting instruments and by rovers on the surface. On Earth, about 90% of atmospheric methane has a biological origin, produced by microorganisms called methanogens. However, geological processes such as serpentinization, the reaction between certain minerals and water, can also generate methane. The challenge is that the concentrations recorded on Mars vary seasonally and even locally, suggesting active sources that have yet to be identified. Determining the origin of this gas is one of the top priorities in Martian science, as its explanation could be directly linked to the presence of life. At the same time, limits must be considered. The surface of Mars is extremely inhospitable to living organisms. Intense ultraviolet radiation, combined with low atmospheric pressure and freezing temperatures, makes the survival of non-adapted life forms virtually impossible. Experiments simulating the Martian environment on Earth show that even resistant microorganisms suffer severe damage when exposed directly to such conditions. Therefore, if life exists today, it is more likely to be protected underground or in isolated microenvironments. Direct exploration of the Martian subsurface is a considerable technological challenge. So far, most rovers have dug only a few centimeters, and deeper drilling probes are still in development. Future missions planned for the next decade aim to drill meters below the surface, where conditions may be more favorable for preserving biomarkers. Ultimately, the question of life on Mars is a puzzle that requires multiple lines of investigation. Martian astrobiology is not limited to answering whether life exists on the planet, but also to understanding how extreme environments can shape and limit biology. This search is not just about Mars, it is also a reflection on life on Earth, its resilience, and the possibility that the universe is full of worlds with similar stories waiting to be discovered. Mars and Earth share a series of characteristics that at first glance make the red planet a natural candidate for comparison and study. However, the differences between the two worlds are equally striking and explain why their evolutionary histories have taken such distinct paths. Analyzing these similarities and differences is essential to understanding not only Mars's past, but also the limits of planetary habitability. One of the most evident similarities lies in the length of the day. A Martian day, Sol, lasts 24 hours, 39 minutes and 35 seconds, just slightly longer than an Earth day. This closeness means that a human on Mars would experience cycles of light and darkness very similar to those on Earth, something relevant to the functioning of the circadian rhythm and biological adaptation. Furthermore, Mars's axial tilt is approximately 25.19 degrees, close to Earth's 23.44 degrees. This tilt gives the planet seasons, although longer due to its Martian year of 687 Earth days. Another similarity is the presence of polar caps. Just like on Earth, they undergo seasonal variations, expanding in winter and shrinking in summer. However, their composition is different. While Earth's polar caps are mainly composed of water ice, Mars's are made up of a mix of water ice and carbon dioxide ice, dry ice, with alternating layers accumulated over millions of years. Despite these similarities, the differences run deep. Mars's atmosphere is extremely thin, with only 0.6% of Earth's sea level atmospheric pressure and composed of about 95% carbon dioxide. This contrasts sharply with Earth's atmosphere, rich in nitrogen and oxygen and dense enough to sustain a moderate greenhouse effect, regulate temperature, and protect the surface from harmful radiation. On Mars, the rarefied atmosphere and lack of a global magnetic field leave the planet exposed to high levels of cosmic and solar radiation, making the surface a hostile environment for unprotected living organisms. Size and gravity also differ significantly. Mars has about half Earth's diameter and only 38% of its surface gravity. This reduced gravity would impact human physiology, potentially causing accelerated loss of muscle mass and bone density during long stays, as well as influencing the behavior of liquids and gases on the surface. For structures and engineering, this is a partial advantage, as it makes it possible to build taller constructions and launch payloads with less energy, but it poses challenges for long-term human health. Geology is another point of contrast. Earth is geologically active, with tectonic plates, constant volcanism, and a dynamic hydrological cycle. Mars, on the other hand, lacks tectonic plates as we know them and presents much more limited and ancient volcanic activity. Even so, the planet hosts geological structures of impressive dimensions, such as Olympus Mons, the largest volcano in the solar system, and Valles Marineris, a gigantic canyon with no Earth equivalent in scale or depth. The climate also shows radical differences. The average temperature on Mars is about -63 degrees Celsius, with extremes ranging from just above 20 degrees Celsius during the day in equatorial locations to -125 degrees Celsius during polar winter nights. These oscillations are far more severe than on Earth, partly due to the absence of large bodies of liquid water to regulate temperature. Moreover, Mars is plagued by dust storms that can envelop the entire planet for weeks, something without parallel in our world. From a hydrological standpoint, liquid water is stable on Earth's surface, whereas on Mars it quickly evaporates or freezes due to low atmospheric pressure. This does not mean Mars is entirely dry. It has vast reserves of ice and possibly liquid briny water in its subsurface, but the availability and accessibility of this resource are far more restricted. Finally, there is the question of life. Earth is the only known planet to harbor abundant life, with complex and diverse ecosystems. Mars, despite past favorable conditions, shows no direct evidence of life so far. This crucial difference demonstrates that even a small deviation in initial conditions or climatic evolution can mean the difference between a fertile world and an inhospitable desert. Comparing Mars and Earth is not just an academic exercise, it is a way to better understand the conditions necessary for planetary habitability, to plan future missions, and even to reflect on the future of our own planet. The similarities inspire us to dream of colonization, but the differences remind us of how unique and irreplaceable Earth is when it comes to sustaining life as we know it. In recent decades, the image of Mars has evolved from a science fiction setting shrouded in mystery to a symbol of real and imminent space exploration. This transformation is deeply reflected in contemporary pop culture, which combines elements of classic fantasy and fiction with recent scientific discoveries and concrete technological advances. Today, Mars is both the stage for epic adventures in film and literature and a plausible destination for human missions in projects already under development. In cinema, one of the most emblematic milestones of this new phase was the film The Martian, 2015, based on the novel by Andy Weir. The production presented a technically detailed and realistic vision of a survival mission on the planet, exploring challenges such as growing food, generating oxygen, and long-distance communication. The film had NASA's consultancy and served not only as entertainment, but also as scientific outreach, sparking public interest in Martian colonization. Another notable example is Mission to Mars Anti 2000, which mixed scientific elements with mystery and fiction, reinforcing the idea that Mars may hold secrets about the origin of life. Television series have also helped keep Mars present in the modern imagination. Documentary and fictional productions, such as Mars 2016-2018 by National Geographic, blend interviews with experts and dramatized storytelling, offering a semi-realistic view of the challenges of establishing a permanent colony. In animation and speculative fiction, Mars appears sometimes as a hostile environment to be conquered, and sometimes as a refuge for humanity in the face of crises on Earth. In the world of games, Mars is a recurring setting, often reinterpreted to suit different genres. Games like Doom use the planet as a battleground against alien forces, while titles like Surviving Mars simulate the construction and maintenance of self-sufficient colonies. These representations allow players to virtually experience the challenges and rewards of living in a world so different from our own. Music has not been left out. References to Mars appear both in lyrics and in album titles, evoking themes of exploration, isolation, or conquest. Some artists use the planet as a metaphor for feelings of distance and estrangement. Others see it as a symbol of the future and innovation. In fashion, advertising, and design, the reddish-orange tone characteristic of Mars inspires color palettes, prints, and technology campaigns. Social media and video platforms play a key role in the constant updating of Mars's image. Photographs sent by rovers, such as the panoramic images of Jezero crater captured by Perseverance, quickly go viral, often accompanied by creative captions or comparisons with locations on Earth. This continuous flow of real images allows the public to follow Martian exploration almost in real time, narrowing the gap between the public and science. On the other hand, Mars still holds space for pure imagination and unproven theories. Even in the information age, ideas of lost civilizations, hidden ruins, or artificial signals continue to appear in forums, books, and videos, proving that the planet remains a powerful catalyst for creativity and speculation. Thus, in modern pop culture, Mars is simultaneously a legitimate scientific destination, a proving ground for human engineering, and a narrative space for stories of survival, discovery, and mystery. This blend of reality and fiction not only keeps the planet alive in the collective imagination, but also helps sustain public and political interest in its exploration, making it increasingly likely that in the future, stories about Mars will no longer be about fictional journeys, but will narrate real chapters of human presence on the red planet. The space race to Mars is, today, one of the greatest technological and scientific undertakings in modern history. Unlike the space race of the 1960s, marked by the bipolar competition between the United States and the Soviet Union to reach the moon, the quest for Mars is a multifaceted effort involving national space agencies, private companies, and international collaborations. The ultimate goal is bold: to send humans to the red planet and eventually establish a permanent presence there. NASA maintains a leading role in this scenario, with a strategic plan that advances in stages. Its robotic missions, such as the Curiosity and Perseverance rovers, the InSight lander and its fleet of orbiters, function as advanced laboratories that collect essential data on the Martian surface, climate, and geology. This information is crucial for planning crewed missions, as it informs everything from landing site selection to assessing available resources, such as subsurface ice deposits. The Artemis program, aimed at returning to the moon, is seen as a technological and logistical stepping stone to Mars, testing life support, propulsion, and habitation systems in an environment closer to Earth before facing the interplanetary challenge. The European Space Agency, ESA, is another major player, working closely with NASA on the Mars Sample Return project, which seeks to bring back to Earth samples collected by the Perseverance rover. This sample return will be a historic milestone, as it will allow detailed analyses in Earth-based laboratories, with the potential to discover evidence of past life. ESA also operates the Mars Express orbiter, active since 2003, which continues to send data about the planet's surface and atmosphere. China, in turn, made a powerful entrance into this race with the Tianwen-1 mission, which placed an orbiter, a lander, and the Zhurong rover on Mars. This integrated approach, unprecedented in Martian exploration, demonstrated the country's technological capabilities, and China now plans even more ambitious missions including a sample return by the late 2030s. India, with its Mangalyaan mission, has already shown that it can reach Mars at low cost, and plans for new missions are underway. Beyond state programs, the private sector plays an increasingly significant role. SpaceX, led by Elon Musk, proposes an aggressive model of Martian colonization based on the Starship spacecraft, designed to transport large payloads and dozens of people per trip. Musk openly talks about establishing a self-sustaining city on Mars, with an initial population of thousands. While many experts view his timelines as overly optimistic, the rapid progress of Starship's flight tests suggests that commercial interplanetary transport could become feasible within a few decades. Other private companies and startups are developing specialized technologies for life on Mars, from systems that produce oxygen from atmospheric carbon dioxide, such as the MOXIE experiment already tested on Perseverance, to methods of growing food in pressurized greenhouses and 3D printing habitats using local materials. Interest in Mars is also fueled by geopolitical and economic factors. Being the first nation or entity to send humans to the planet and keep them alive safely would be an unparalleled achievement, with diplomatic, technological, and commercial implications. At the same time, the prospect of exploiting natural resources, such as rare minerals or even water to supply future interplanetary routes, adds a strategic dimension to the race. Despite the enthusiasm, the challenges are immense. More efficient propulsion systems must be developed to shorten travel time, habitable modules capable of protecting against radiation, reliable methods of producing food and water, and strategies to handle the extreme psychological isolation of crews spending years away from Earth. Ethical questions such as the possibility of biological contamination of Mars or the environmental impact of its colonization are also at the center of debates. Thus, the space race to Mars is not only a technological competition, it is a testament to humanity's ability to cooperate and compete at the same time, to transform ambition into engineering, and to expand the limits of what it means to live beyond Earth. Each step taken, whether landing a new rover or testing a reusable rocket, brings us closer to a historic moment that, when it happens, will redefine humanity's presence in the cosmos. The idea of transforming Mars into a habitable planet for humans, a process called terraforming, is one of the most ambitious and debated concepts in space exploration. Popularized by works of science fiction and defended by some scientists and entrepreneurs, terraforming involves deliberately modifying Mars' climate, atmosphere, and surface to make them more similar to Earth's. This proposal, which combines science, engineering, and imagination, raises questions about technical feasibility, timelines, costs, and ethical implications. From a theoretical perspective, the central goal of terraforming Mars would be to increase the planet's average temperature and thicken its atmosphere, creating conditions that would allow the stable presence of liquid water on the surface. Currently, Mars' atmosphere is extremely thin, only 0.6% of Earth's atmospheric pressure, and is composed mostly of carbon dioxide. The average temperature is about -63 degrees Celsius, making human life impossible without protection. Several methods have been proposed to initiate this process. One of the most discussed is the release of greenhouse gases, such as carbon dioxide, methane, and chlorofluorocarbons, to trap more heat from the sun. The CO2 already present on the planet, stored in the polar ice caps and subsurface, could be released by artificial heating, using giant orbital mirrors or nuclear reactors on the surface. Another theoretical method is to impact Mars with asteroids or comets rich in ammonia and ice, which would release heat and additional gases into the atmosphere. There are also bolder ideas, such as installing enormous space mirrors to concentrate sunlight on the Martian surface, or creating an artificial magnetic field strategically placed at Mars' L1 Lagrange point, protecting it from the solar wind and allowing the atmosphere to accumulate over centuries. NASA studies published in 2017 suggest that this magnetic approach could be one of the most effective steps to preserve and increase Mars' atmosphere in the long term. However, terraforming faces enormous obstacles. A 2018 study led by Bruce Jakosky and Christopher Edwards concluded that there is not enough carbon dioxide on Mars to create a greenhouse effect capable of sustaining liquid water, even if all available CO2 were released. This means that enormous amounts of gases would need to be imported from other celestial bodies, requiring technology and energy on a scale far beyond our current capabilities. Furthermore, the process would take centuries or millennia to achieve significant results, even with advanced methods. Another challenge is the ethical and environmental impact. Altering an entire planet raises questions about planetary preservation and humanity's right to modify another world. If native microbial life exists, even if subterranean, terraforming could destroy it or alter it irreversibly. Many scientists argue that the priority should be to study and understand Mars as it is before attempting to transform it. Still, the idea of terraforming Mars remains alive in the human imagination, fueled by visions such as those of entrepreneur Elon Musk and novels like Kim Stanley Robinson's trilogy, Red Mars, Green Mars, and Blue Mars, which explores in detail the process, its challenges, and the social and political changes involved. In the scientific field, studies continue to investigate forms of partial terraforming, that is, creating localized habitable environments, such as domes, greenhouses, and pressurized cities, without modifying the planet as a whole. In practice, the first stages of Martian terraforming will likely be local and controlled, using in situ resources to sustain small human colonies. This may include melting subsurface ice for consumption and agriculture, generating oxygen from atmospheric CO2, and creating greenhouses protected from radiation. Even if a global transformation is never achieved, these technological advances will be essential for long-term human presence. Thus, terraforming Mars remains on the threshold between science and fiction. The basic concepts are scientifically plausible, but their execution depends on technologies, resources, and political decisions that may be centuries away. Even so, discussing and studying the subject is not a waste of time. It forces us to think about planetary engineering, sustainability, and the ethical limits of our expansion through the cosmos. The colonization of Mars is one of the greatest challenges and dreams of contemporary space exploration. More than just visiting the red planet, the goal would be to establish permanent, self-sufficient human settlements capable of surviving, thriving, and eventually expanding. To make this a reality, a complex set of issues must be resolved, involving engineering, biology, psychology, logistics, and even ethical and legal aspects. The first challenge is interplanetary transport. Trips to Mars depend on launch windows that occur approximately every 26 months, when the distance between the planets is shorter. Even in the most favorable conditions, a trip can take between 6 and 9 months, depending on the propulsion technology used. This requires spacecraft capable of sustaining crews for long periods in microgravity, with water and air recycling systems, protection against cosmic radiation, and food reserves for the entire journey. Faster propulsion technologies, such as nuclear thermal or electric engines, could reduce travel time and minimize risks. Once on Mars, the second major obstacle is safe landing. The thin atmosphere makes it difficult to use parachutes to slow down large payloads, and the entry, descent, and landing (EDL) process for multi-ton vehicles is still a technological frontier. Missions like Perseverance used sky cranes and advanced heat shields, but transporting heavy habitat modules and large supplies will require significantly scaling up these capabilities. Survival on the Martian surface means facing three main environmental factors: reduced gravity, radiation, and low atmospheric pressure. Gravity at only 38% of Earth's can impact long-term health, leading to loss of bone and muscle mass, alterations in the cardiovascular system, and possible unknown effects on human development if colonies include children in the future. Radiation is even more critical. Without a global magnetic field and with a thin atmosphere, Mars exposes its inhabitants to cosmic radiation levels that, over just a few decades, would considerably increase the risk of cancer. Proposed solutions include underground habitats, covering with layers of local regolith, or building domes shielded by water or special polymers. The issue of resource production is another cornerstone of colonization. Bringing everything from Earth would be logistically impossible and economically unfeasible. That's why the idea of in situ resource utilization, ISRU, is central. This includes extracting ice to obtain drinking water and generate oxygen, growing food in pressurized greenhouses using artificial lighting and treated substrates, and manufacturing bricks or structures from Martian regolith using 3D printing. Experiments like MOXIE on the Perseverance rover have already demonstrated that it is possible to produce oxygen from the carbon dioxide in the atmosphere. Supply logistics will be a constant challenge in the first decades. Even with local production, initial colonies will depend on regular shipments from Earth, including spare parts, medicines, and high-complexity nutritional foods. This requires a reliable interplanetary transport fleet and precise coordination to avoid critical shortages. The psychology and sociology of life on Mars are also crucial topics. Isolation, confinement, and delayed communication with Earth, from 4 to 24 minutes per message depending on the distance, can lead to stress, anxiety, and interpersonal conflicts. Habitat design should prioritize not only functionality, but also comfort, and provide visual and social stimuli to reduce the impact of prolonged isolation. Martian communities would need to develop cultural and political autonomy, defining rules of coexistence and governance, especially as the population grows and diversifies. Another key point is the colony's economy. At first, Mars will be an expensive project supported by governments, private companies, and international partnerships. In the long term, it will be necessary to find means of economic sustainability, whether through mining rare resources, space tourism, or offering exclusive scientific and technological services. There is also debate over ethics and planetary preservation. If Mars harbors native microbial life, its colonization could mean irreversible contamination of those ecosystems, raising dilemmas about the right to explore and modify another world. On the other hand, colonization could also serve as an insurance policy for humanity's survival, ensuring that a catastrophic event on Earth would not mean our extinction. Life on Mars will therefore be marked by a combination of self-sufficiency and interdependence, technological innovation and human adaptation. Even if the first settlements are small, each milestone, such as the first functioning greenhouse, the first baby born on Mars, or the first export to Earth, will have profound historical significance. Martian colonization will not be a single event, but a gradual process, built over decades of experience, mistakes, successes, and constant learning. Establishing a human presence on Mars will not only be a technological feat, but also an endeavor filled with risks and obstacles that must be rigorously assessed. While the image of self-sustaining Martian colonies is inspiring, the reality involves dealing with a relentless environment, limited resources, extreme isolation, and dangers not yet fully understood. These challenges are broad and interconnected, ranging from physical and environmental issues to psychological and social aspects. The first major risk is radiation. Without a global magnetic field, and with an extremely thin atmosphere, Mars exposes any living being on its surface to levels of cosmic and solar radiation far higher than those on Earth. Estimates indicate that the annual radiation dose on Mars is about 2.5 times greater than at the top of Earth's atmosphere, enough to increase cancer risk, damage tissues, and compromise biological systems in the long term. The only way to mitigate this risk is to build protected habitats, either buried under regolith covered with layers of ice, or designed with materials that absorb radiation effectively, such as hydrogen-rich plastics and metallic composites. The second challenge is reduced gravity, equivalent to only 38% of Earth's gravity. We still do not know the long-term physiological effects of this condition. Experience with microgravity in space stations shows muscle mass loss, decreased bone density, changes in the cardiovascular system, and impacts on balance and vision. Although Martian gravity is greater than that of deep space, it is likely that intense exercise regimens and specialized equipment will be necessary to maintain the colonists' physical health. Extremely low atmospheric pressure and an average temperature of 63 degrees Celsius make any exposure to the external environment lethal within minutes without a spacesuit. The constant need for pressurized suits for outdoor activities limits mobility, increases the risk of accidents, and requires continuous maintenance. Failures in life support systems, such as oxygenation and carbon dioxide removal, can have immediate and fatal consequences. Another critical risk is resource scarcity. Although it may be possible to extract water ice and minerals from the soil, local production will be limited in the early stages. Dependence on supplies from Earth will mean vulnerability to launch failures, logistical delays, and technical setbacks. A transportation failure during a launch window could mean months of waiting until the next opportunity, putting lives at risk. Biological contamination is a concern in both directions. The possibility of introducing Earth microorganisms that could affect any native microbial ecosystem, and the risk of bringing unknown Martian microorganisms into human habitats, where they could have unpredictable effects. Strict quarantine and sterilization protocols will be essential to protect both Mars and the colonists. Psychological and social isolation may be one of the most underestimated challenges. Communication with Earth will have a delay of up to 24 minutes for each message, making real-time conversation impossible. Physical distance and the lack of rapid return in an emergency create a constant feeling of vulnerability. Interpersonal conflicts, depression, anxiety, and mental fatigue can worsen in closed environments with little privacy. Designing habitats that provide comfort, visual stimulation, and social interaction will be as important as ensuring technical functionality. Extreme environmental events also pose threats. Global dust storms, capable of covering the entire planet for weeks, can reduce solar energy generation, impair communications, and damage mechanical systems. Although Martian winds exert less physical force due to low air density, the fine electrostatically charged dust can infiltrate equipment, clog filters, and erode surfaces. In addition to these factors, there are ethical and legal challenges. Issues such as territorial sovereignty, property rights over natural resources, and international regulations to prevent environmental damage on Mars have yet to be defined. Governing a distant colony will require new political and legal structures, possibly different from those on Earth. Finally, it must be considered that even with all the planning, the unknown will always be a risk. Geological phenomena not yet understood, unexpected climatic variations, or catastrophic system failures can occur. Mars is an environment that does not forgive mistakes. Any failure can have irreversible consequences. Overcoming these challenges will require not only cutting-edge engineering, but also strategic planning, international cooperation, and human resilience. If successful, Martian settlement will be definitive proof of our species' ability to adapt and thrive in a radically different world. The future of Mars is a territory where science and imagination meet in an inseparable way. Over the past few decades, technological advances and scientific discoveries have transformed the Red Planet from a distant and unattainable destination into a plausible target for human exploration. Even so, what exactly will happen to Mars in the coming decades and centuries remains open to multiple possibilities, some anchored in concrete plans, others still confined to the realm of visionary ideas. In the scientific and technological field, the coming decades are expected to be marked by sample return missions, such as the ambitious Mars Sample Return Program, developed in partnership between NASA and ESA. These samples, collected by the Perseverance rover, may provide definitive answers about the presence of past or present microbial life. In addition, new orbiters and rovers should expand geological mapping, atmospheric analysis, and the search for underground water reserves, all vital information to prepare for human arrival. The boldest prospect is the arrival of the first crewed missions, which may occur between the 2030s and 2040s, according to optimistic predictions. These missions will focus on establishing temporary scientific bases, testing survival technologies, and exploring the ability to produce resources locally, such as oxygen, water, and fuel. This will be the turning point. If these operations succeed, the transition to permanent settlements may gain momentum. In parallel, Martian colonization is seen by some visionaries, such as Elon Musk, not just as a technological goal, but as an existential necessity. The idea of making Mars a second home for humanity, a backup for civilization, is driven by concerns over catastrophic events on Earth, such as asteroid impacts, extreme climate change, or global conflicts. In this vision, self-sufficient Martian cities could shelter millions of people in a distant future, with their own economies, Martian culture, and even an independent political identity. However, there are more moderate perspectives that envision Mars as a permanent scientific outpost, similar to the International Space Station but on a planetary scale. In this model, there would be crew rotation, smaller colonies, and a focus on research, resource mining, and support for even more distant missions such as to the asteroid belt and the moons of Jupiter and Saturn. There is also the field of partial terraforming, which proposes the creation of localized habitable environments, pressurized domes, adapted caves, and large-scale greenhouses, without trying to alter the entire planet. This could provide a relatively comfortable quality of life for thousands of people, while preserving the Martian environment for scientific study. Popular imagination will continue to play an important role in this future. Films, series, books, and games will continue to project visions of Mars that influence the public and even inspire engineers and scientists. Some of these works visualize a verdant, transformed, and fertile Mars. Others, an arid world but vibrant with human life, adapted to its original conditions. This constant exchange between fiction and science has already shaped in the past our relationship with the planet and will continue to do so. However, the future of Mars does not depend solely on technical advances. Political, economic, and ethical factors will play a central role. The governance of a Martian colony, the definition of laws and rights, the preservation of possible native life forms, and the division of resources between nations and private companies will be the subject of intense debates. Without clear and collaborative agreements, Martian occupation may face disputes similar to those that already occur on Earth. Ultimately, Mars is more than a physical destination. It is a symbol. It represents our ability to dream big, to overcome barriers, and to seek a future beyond the planet that gave us birth. Whether as a scientific base, a thriving colony, or a partially terraformed planet, its fate will be tied to the best and worst of humanity, our creativity, our ambition, our curiosity, and inevitably, our conflicts. Whatever the scenario, one thing seems certain: the story of Mars and humanity is now intertwined. Every step we take toward the red planet will also be a step toward a new phase of civilization, in which living on more than one world will cease to be fiction and will become part of our reality. Mars has always been more than just a bright point in the night sky. For millennia, it has served as a mirror in which humanity has projected its fears, hopes, curiosities, and ambitions. From the earliest naked-eye observations made by ancient civilizations to the high-resolution images sent by probes and rovers, the red planet has been a constant presence in the human imagination, at times as a symbol of war and destruction, at others as the promise of a new beginning. The fascination with Mars is rooted in its balance between familiarity and strangeness. It is similar enough to Earth to spark the feeling that we could live there, yet different enough to challenge us to rethink what we understand as home. Its grand geography, with colossal volcanoes, immense canyons, and polar ice caps, contrasts with the fragility of its thin atmosphere and extreme climate, reminding us that beauty and hostility can coexist in the same world. From a scientific perspective, Mars is a living archive of the history of the solar system. Its rocks and sedimentary deposits hold records of a past in which water flowed freely, of a climate that changed radically, and perhaps even of forms of life that once existed. Studying Mars is also a way to study early Earth, understanding how similar worlds can take vastly different paths. Every discovery about Mars is, in some way, a discovery about ourselves. But Mars also forces us to reflect on our choices. The possibility of colonization and exploration raises profound questions about responsibility, ethics, and preservation. If we find life, even microbial life, we will have to decide whether our right to expand outweighs our duty to protect a native ecosystem. And if we do not find life, it will be up to us to decide what kind of human presence we wish to establish. One that repeats the mistakes of exploitative exploration, or one that inaugurates a new chapter of balanced coexistence with another world. The race to Mars is also a test of our capacity for cooperation. While competition between nations and private companies drives innovation, long-term success will depend on coordinated efforts and the sharing of knowledge. The red planet could become both a symbol of global unity and a stage for disputes over prestige and the resources it may offer. Ultimately, humanity's relationship with Mars is, at its core, a story about self-knowledge. In seeking answers about the planet's past and present, we are trying to answer fundamental questions about our own existence. Are we alone? Are we capable of living beyond Earth? And if so, What will we carry with us? Only our technology, or also the wisdom we have accumulated? Mars reminds us that we are a species in motion, always looking beyond the horizon, even when we do not yet have all the answers. It is the next logical step in our exploration, but also a reminder that each technical advance must be accompanied by an ethical one. The red planet, silent and distant, reflects not only the light of the sun, but also the light and the shadows of humanity. When we finally set foot on its soil, we will not just be marking territory on another world. We will be writing a new chapter in our history, one that future generations may read as the moment we ceased to be a species confined to a single planet and became, truly, citizens of the cosmos. If you have made it this far in our journey through the red planet, subscribe to the channel to keep following our scientific documentaries. Leave your like, share this video with anyone who also loves science, and tell us in the comments your opinion about Mars. Which part of this story impressed you the most? And also let me know which city you are watching from. I'd love to know how far this journey has reached. Your participation is what keeps this project alive and motivates us to bring more and more content like this.